Good afternoon, class. Today we're going to look at solving exponential and logarithmic equations. Switch over to my paper. Okay, we're looking at two broad topics here. First of all, solving exponential equations and then solving logarithmic equations.
Are you going to review that they've already solved exponential equations before?
They solved a few logarithmic equations the last time also. It's too bright in here.
Oh yeah, let me dim the light.
There are two methods, two generally accepted methods of solving. Don't make it too dark, Tony.
Can you not see?
I guess I can. Roman numeral 1, that same base method. Do y'all remember that? Oh, I don't even have my microphone. Thanks for reminding me. You see, I'm too interested thinking about our auto break-in. I forgot to get my microphone ready. Let's see. Okay. So the first method is the same base method. We saw that 2 assignments ago. The same base method. Y'all recall that? Something like 2 to the x is equal to 8. 2 is a prime number, so we're not going to write 2 as a power of anything other than 2, but we can change the 8 to a power of 2 as 2 cubed. You would get the same base on both sides, and once you have the same base on both sides, you drop the base, set the powers equal to give x equals 3. Do y'all remember that? Okay. And I said that if it was impossible to get the same base, there was a method of solving that used logarithms. And so, Roman numeral 2, we'll use this for unlike bases. If you cannot get a common base on both sides, what you can do is use logarithms. You can take it doesn't matter which logarithm you use, but you need to use a logarithm that has a key on your calculator. The one that I use, I'm going to use the natural log of both sides. And the reason you take that natural log is because then that lets you bring down the exponents. Bring down exponents using that power rule of logarithm. And if you have, let's say the variable is x, you have to isolate the x term on one side. Isolate x on one side. If you have more than one x term, you'll have to get all of the x terms on the same side and factor out the x. I'll say, I'm going to put that as a parenthetical statement. Isolate x on one side, so I'm going to say, if you have 2 x terms, get the x terms on the same side and factor out the x. You'll see what I mean in a moment. Get the x terms on the same side of the equation. I could have already done the first problem rather than writing out these steps. Get the x terms on the same side and factor out the x. That's that parenthetical statement that I added on to step 3. And step 4, to get x by itself, at this point, you'll have to divide. And to illustrate, we'll look at number 1. Hopefully this only has one, the first one should only have one x term. Hey, look at that. That's just a coincidence. 2 to the x equals 7. The example I made up for the same base method, switch back to my paper.
I wanted to mention something. Be sure to look at these instructions every time. It isn't always going to say round to 4 decimal places. And if you mess up on a homework, okay, but you don't want to miss a problem on the test because you rounded to 4 decimals when it's only asking for 3. Okay?
Switch to my paper. So notice 2 to the x equals 8. We were able to get a common base of 2. But looking at this number 1, 2 to the x equals 7. Notice how I wrote the problem down. I left some space in front of both sides. I think we can, 2 is a prime number, you can't change it. 7 is a prime number, you can't change that. So I think it's pretty easy to convince ourselves that that we cannot get a common base. So we have unlike bases, so we're going to take the natural log of both sides. Then we'll bring down the exponents. In this case, there's only one exponent. That's the nicest possibility. So we'll have x times the natural log of 2 is equal to the natural log of 7.
The x term is isolated.
The x term is already isolated. Notice that's the only term there. That's saying x times the natural log of 2. ln2 is just a messy decimal number. You have a number times ln2, so we divide to get x by itself. You have a number times ln2. What undoes multiplication? Division. Divide by ln2, divide by ln2 to give you x equals ln7 divided by ln2. If they wanted the exact answer, this is what you would have to type in. But they want a decimal approximation to solve exponential equations with unlike bases. I should stick on a 5th step. You'll have to use your calculator to get a decimal approximation. So once you divide, I guess the 5th step I'm going to stick on is use calculator. So I'm going to put a little wavy equal sign there to mean that what I'm about to write is an approximation. Let's punch in ln7 divided by ln2. Remember that at least our calculator and most calculators, when you press that logarithm key, it is going to open a parenthesis for you. You have to be sure to close that parenthesis or you're going to get the wrong answer. If your calculator when you press that ln for the 2, if it opens a parenthesis, you're going to have to close it. So we have ln7 divided by ln2. They want it rounded to 4 decimal places. It's a 2.80. Is that going to stay a 7.3 or is it going to go up to a 7.4? Which one? Usual rules for rounding. 7.4. Good.
Yes.
Good.
If the digit after the 3 is a 5 or bigger, you round it up.
Otherwise, you just drop those other digits. So 2.8074.
So wow, 2.
Well, 2 squared would be 4. 2 cubed is 8. So it makes sense that the answer should be between 2 and 3. So if you took type
the whole thing,
it would have been exactly 7.
Okay, so
typing in the answer. 2.8074.
Any questions on that? Notice he didn't do any of this parentheses stuff because there was only one x, not
Now,
two
what
x
happens if
terms.
we have two x's? I bet you on the second problem we're going to have two x terms. Let's see. Yes. Let me write this down. Number 2.
See how there's two different x's? So we're going to have to do that parentheses stuff that he talked about in there.
2 to the 7x plus 2 is equal to 7 to the x. 2 to the 7x plus 2 is equal to 7 to the x. So let's switch over there. Once again, 2 and 7, you can't get a common base there, so we'll stick an ln in front of both sides. The reason we stick that ln is so we can use the power rule to bring down the exponent. Realize that entire exponent has to be multiplied by ln2. So as I bring down that 7x plus 2, notice I'm enclosing it in parentheses, times ln2 equals, here we have an x, we'll pick up the x and bring it down, times ln7. We use the power rule of logarithms to bring down the exponents. On the right side we have x times ln7. On the right we have x times ln7, but look at the left. On the left side we have ln2, that's a number. It's a number times 7x plus 2. You have a binomial times a number. You have a binomial times a number. 7x plus 2 times ln2 would be maybe a 1 point blah blah blah, but it's a number times 7x plus 2. What do we do to get rid of the parentheses there? We're going to have to distribute. Distribute the ln2 over the 7x, and then the ln2 times 2. A word of advice, do not get creative when distributing. When distributing, 7x times ln2 is just 7x times ln2 plus 2 times ln2 is just 2 times ln2. We still have that x ln7 on the left. We need to get the x terms on the same side. You know what I think would be easy? I think it'd be easier to move this x term over to the right. Otherwise, we'd have to move this x ln7 to the left. We have to move the thing that doesn't have an x to the right. You're picking up a lot of minuses there. If you leave that 2 ln2 where it is, leave that 2 ln2 where it is, we have an x ln7. I don't see a sign in front of that plus, so what do I assume it is? I mean, in front of that 7. I don't see a sign in front of that 7, so what do we assume it is? A positive. So we move it over, it becomes a minus 7x ln2.
Why don't you look at your
Let's look back at what I said. I said, if you have two x terms, get the x terms on the same side. We've done that. And now it's factor out the x. So we still have this 2 ln2 equals, we're going to factor out an x. Notice both of those terms have x's. We moved them over to the same side. So we're factoring out that x. That's going to leave me an ln7 minus What are we going to be left from this term here? We have that minus 7 times ln 2, correct. So I said, get the x terms on the same side and factor out the x. We're now ready to divide. What is x being multiplied? Unfortunately, x is being multiplied by that messy ln 7 minus 7 ln 2. So we're going to divide both sides. ln 7 minus 7 ln 2. Divide ln 7 minus 7 ln 2. That cancels out, so we're left with x equals, I'm going to write it big. It's a 2 ln 2 on top, divided by ln 7 minus 7 ln 2. And notice the fifth step, we have to use our calculator. You need to make sure that your calculator does what you want it to do. With these messy calculations, what you want is you want it to simplify the numerator, simplify the denominator. The last operation is that division. To make sure that your calculator does what you want it to do, you're going to have to assume parentheses around the numerator and the denominator. If you're trying to type in a fraction that has any operation other than division, look at number 1. It was ln 7 divided by ln 2. There was no multiplication. There was no addition or subtraction. Oh, wait, y'all couldn't see this? Yeah, you're right. For this first one, there was number divided by number. There was no addition, subtraction, or multiplication taking place. So we didn't need those extra parentheses around the top and the bottom. But
if I can interrupt for just a moment. If you had something like 5 plus 5 divided by 2 plus 8, y'all know what that answer would be. I think you could do it in your head.
It's 10 over 10, which reduces to what? 1. Punch it into your calculator without parentheses.
5 plus 5 divided by 2 plus 8. 13. Is it going to give us 15.5?
That's C.
Am I doing that right?
Press and C.
Yeah.
That's wrong, isn't it? You need to make sure that it simplifies the numerator, simplifies the denominator, and the last operation that's performed is that division. To do that, you have to include those parentheses around the top and the bottom. But it gets trickier because whenever I press an ln, what's going to happen? I'm going to get a parenthesis there too. And I have to close that parenthesis. So we're going to have nested parentheses that we're typing in. Here you're going to have parenthesis ln. It's going to, when you press ln, it's going to spit out a little parenthesis. You have to close it. There's another set of parentheses. Where will I need another set of parentheses when I'm punching all this stuff in? Okay, that 2 there. So look at how Tony's going to punch that in.
If there's more than one number on top, put it all in parentheses. And there's 2 numbers on top, a 2 and a 2. If there's more than one number on the bottom, put it in parentheses. 1, 2, 3 numbers on the bottom. So
that's a good way of thinking of it. I've never heard you say that before. Okay.
I was just thinking of it as you were saying that.
ln. Notice it opened a parenthesis. He's going to type that 2.
And here's the common mistake. Students don't put the 2 parentheses there. If you don't put the 2 parentheses there, you're going to get some sort of error.
Oh, well, no, you'll just get the wrong answer.
You'll get a wrong answer.
Divided by. Now we're ready. We're going to the denominator. That little slash went to the denominator. It's ln 7, close parenthesis, minus 7 ln 2. Close. Now, on this calculator that we're using, if you don't close those final parentheses, it'll automatically close them for you. And so you're okay. But that's not true for all calculator models. So, and I have a aversion to dangling parentheses. That's what they're called in programming. I didn't see the answer.
It doesn't matter. What do the instructions say? How do we round it?
3 decimal places now, okay?
Yeah.
So
Now.
let's type in, let's see, it's a negative. So we get x equals negative 0.4. Is it going to be a 7.7 or a 7.8? Stays as 7, yes.
You look at the number after that second 7, the 0.
So we just drop those remaining digits. It's called truncating. We type in negative 0.477.
Negative is, let me move my calculator. Negative 0.477. It's theoretically possible that you could punch in this stuff and get some sort of error warning, non-real number or something. If that happens, then more than likely you messed up. But if not, then that's what this part answer is here. And we'll see that more in later on. Okay? Did I check it? No, I didn't.
Any questions? This is a powerful method of solving exponential equations because it'll work even if you could get a common base. When you have a chance, stick an ln in front of both of those, you get ln 8 divided by ln 2, then that's going to get reduced to 3. So even with the same base method, this unlike base method does work.
See, I punched it in.
Oh, look, ln 8 divided by ln 2. That little example I made up and I got the same base. There it is, 3. Isn't that what Tony's calculator said when he took the natural log? Okay, number 3.
Oh, we're going to number 3.
Oh, 6 to the x plus 2 is equal to 4 to the 2x minus 1. Ah, 6 is divisible by 3. 3 doesn't go evenly into 4, so there's no way we're going to get a common base. So we'll introduce, that's something you may want to remember. If you have to use logarithms on these exponential equations, they're going to tell you how to round. They'll tell you, if you're having to take the common base of, the natural log of both sides, they're going to tell you have to round your answers. So that's something you might want to remember.
Bad as me telling them to look at the instructions.
Well, I'm not that bad. Okay. So, but we take the natural log of both, switch me over, and then I bring down the x plus 2 times ln 6 is equal to, bring down the 2x minus 1 times ln 4. I want to show, before I go any further on this, there's an observation I should have made with number 2, and I failed to make it. And it's important. It'll help you spot errors. When I stuck the ln in front of both sides, I picked up 2 arguments, 2 and 7. Remember, the argument is the thing that follows the logarithm notation. I have ln 2's, I have ln 7's. That's all I can have in my answer. I can't have ln 14. I can't pick up an ln 9. Everything that I typed in, it was only ln 2's and ln 7's. So if you're going along and you start off with an ln 2 and an ln 7, and a few minutes later you have an ln 5, you're doing something wrong. All you can have in your answer that you're typing into the calculator are ln 2's and ln 7's. So that means in a moment I'll have a big messy fraction to punch into my calculator. The only LNs I can have though are LN6 and LN4.
And that's why you have them in red.
LN6 and LN4. That's all you can pick up in your during this process. Now we have to distribute. X times LN6 is X LN6. Don't get creative. There's nothing creative about this. 2 times LN6 is just 2 times LN6. It's not a LN12. I guess you could move the 2 up and make it LN36, but why would you want a bigger argument? Equals, you call out what I'm going to have on the right. You have to distribute again. I'm waiting. LN4, good. Minus, okay, 1 times LN4 is just an LN4. Good. We have to get all of the x terms on the same side. Here, when there's 4 terms, I go back to my old prejudice of always getting the x on the left side. So I think I'm going to gather the x's on the left. Yeah, I have an XLN6 already. I have an XLN6. I'm going to pick up this 2XLN4 and move it over. What sign am I going to get when I do that? Negative, I agree, because that's an assumed positive. So it moves over, change the sign. That's a 2XLN4. I already have a negative LN4 on the right. What else am I going to have here? I need to move that term over to the right. I need to move this term over to the right. I have the negative LN4. I've already written that down. What else am I going to have here? Minus 2 LN6. Any questions on our... Oh, wait a minute. What did I forget here? That's why y'all got so quiet.
Oh my goodness.
What did I forget? I forgot the X. Thank you. Y'all silence said it. Okay, that made me... That was a 2X LN4. I don't like that. That's too messy. I'm going to recopy it. Minus 2X LN4 equals a negative LN4 minus 2 LN6. There, let me just mark that line out. We've got all the x terms on the same side. Once we get the x terms on the same side, what's our trick?
Got to write it with just one x.
You get the x terms on the same side and factor out the x. So now we're going to factor out this x. Taking out that x,
just cover up the x.
And what are we going to be left with inside those parentheses? Here. I'll get us started. We're going to have an LN6. What else will we have?
Cover up that x.
Cover up that x. What have we got left? Minus 2 LN4. Good. Once you've factored out that x, what do? You want to get rid of that x times this messy stuff. What are we going to have to do to undo that times? Divide by LN6 minus 2 LN4. LN6 minus 2 LN4. So here's what we're going to have to punch into our calculator, and it's messy. Negative LN4 minus 2 LN6 on top, and LN6 minus 2 LN4 on bottom. What do y'all think? Am I going to have to enclose the top and bottom in parentheses to make sure I get the correct answer? Yeah, I'm going to have to enclose that top and bottom. Remember, if you have any operation other than something divided by something, we have subtraction. That's a 2 times ln 6. So we have multiplication, subtraction. We're definitely going to have to enclose the top and bottom in parentheses.
And what I would say is 3 numbers on top. 1, 2, 3. 3 numbers on the bottom. You better have parentheses around the top and the bottom. But there's a lot more parentheses. Where do
When
they
we
go?
press that ln, it's going to open a parenthesis, so we have to close it. And then that's a -2. It's going to open a parenthesis. We have to close it.
If you don't have these 2 parentheses here, it's going to count it wrong.
No, it's going to give you the wrong
It's going to give you
answer.
the wrong answer, not count it wrong.
Okay. Open. It's going to open there, so we have to close it. Any other parentheses needed? Around that 4. It'll open and close.
Now, on my calculator, I have 2 minus keys. This is the subtraction key, and this little minus down here, can y'all see that, is the
Negative key.
Negative
Look
key.
at the first. Press. Okay, go ahead and get started. Do the parenthesis first.
Wait,
Oh,
it's
you're making it bigger, good.
Okay, parentheses.
Turn it on.
Oops, turn off.
Parentheses. What is he going to press? That symbol there. What symbol will he use? There are 2 dashes. There's that blue dash he's circling and showing the other one.
That's subtraction. This is negative.
In math, we use negative and subtraction. We use plus and positive interchangeably. But from a calculator point of view, they're different. Well, plus is the same thing, okay? But in this case, the negative key is what you want. Notice it's a negative, and then ln 4, close parenthesis, minus, and notice the negative and the minus keys look different on this calculator. The negative is a little bit smaller and lifted up more, okay? So this middle symbol is a minus, 2 ln 6,
Gotta put the 2
close,
parentheses.
close, divided by, left parentheses, ln, open the parentheses, so type that 6 and close it, minus 2 ln 4, close, close.
Oh, and how did it say?
Oh,
to
how did
round
it say to round? How did it look?
Oh, it says round to the nearest 1,000.
How many digits is that? Tenths, hundredths, thousandths. That's 3 digits. So we're rounding to 3 decimal places. 5.06. Is it going to stay a 6 or go up to a 7? That's second 6. Does it stay a 6 or go up to a 7? I can't hear you.
Someone said it goes up to.
That goes up to a 7. Because after that 1,000th spot, there's a 9. It's bigger than 5, so goes up. So 5.067. Any questions there?
Here, come back over here.
5.067.
7. And just for illustration purposes, I want to show something.
What are you trying to show? Oh, if you went back and replaced that minus, that negative with a minus symbol, or what?
Okay. All I did was change the ln 4 at the very end to ln negative 4, and look what it's going to say. Error, non-real answer. There was another time this semester when my calculator would say that non-real answer. If it's not a real number, it has to be a what? It starts with an I.
Imaginary. Imaginary. It could be irrational numbers are still real numbers, so
It's
imaginary.
Imaginary numbers, that's where you get these non-real answers. That's why they give you this, they might say the solution is the empty set. I think earlier
That
it
can't
said
happen though, unless
not
the
a real
base.
number.
The only way that would have happened is if the base is negative. And when we started discussing exponentials, we said that the base must always be positive and it can't be 1. So you shouldn't wind up with a negative argument for these exponential equations.
So there shouldn't be a negative after the ln.
Okay, number 4.
Oh, this has a letter E in it. I bet this is the worst one.
0.092 e to the negative 0.09t is equal to 0.06.
Remember, E is approximately 2.718281828.
Okay, switch to my paper. This is actually going to be a very nice problem. We stick the ln in front. Remember, we were solving equations like this back in the exponentials assignment, and I said if you have e as a base and you're trying to get a common base, you better have an e on the other side. And we don't have an e on the other side. So that means we have to use this unlike base method. And so on the right-hand side, we have an ln 0.06. On the right, we have an ln 0.06. What do we have on the left?
You'll have to remember the last assigned problem, the last problem we did in class on Wednesday?
Wednesday, yes.
What happens when the
No,
ln...
it was on Monday.
Monday, you're right. What happens when the ln and e are side by side like that?
What happens when the ln and e, we said ln and e are inverse functions, and when they're performed consecutively, what happens? They cancel themselves out. So this right-hand side here, this left side, we're not going to be bringing down that exponent using the power rule. We're going to cancel out those inverse functions, and that leaves us with just a negative 0.09t.
Now, if you'd used LOG on this, oh wow,
Yeah.
they wouldn't have canceled out.
Mm.
Another reason to use ln when solving exponential equations, not LOG. Earlier.
Okay. So I think there's only one step left here to get t by itself. What are we going to have to do? That t is being multiplied by a negative 0.09. We're going to divide by the coefficient negative 0.09, negative 0.09. So here's what we got to punch into our calculator. It's a fraction. ln 0.06 on top and negative 0.09 on bottom.
There's only one number on top, only one number on bottom.
We don't have to put the parentheses around the top and the bottom. It's not wrong to do that. It's never wrong to write parentheses around the top and bottom.
And to punch it in.
And to punch it in, that's what I mean. It's never wrong. It's just not necessary. I'll tell you, there is a set of parentheses we're going to have to use. Where's that parenthesis? Okay. Because of that ln. It's going to open a parenthesis. You have to close it.
If you don't close that parentheses, you're not going to get the right answer.
Punching that in, we get
0.06.
Right parenthesis divided by.
This is a negative, so it's that little minus in the parentheses.
Negative 0.09.
0.09. I got to put that first zero. Ooh, and how are we told to round
Yeah,
this?
I forgot to look.
Typing it 4 decimal places.
Okay, so that's approximately. So we have a 31 point. It's either going to be 2601 or 2602. Which one's it going to be?
Give them a moment to catch up.
2601.
I agree.
The number after that first one is another one, so just drop it. And just for illustration purposes, 0.06. If I hadn't put the
If you hadn't closed that parenthesis after that 0.06,
all I did was not close the parentheses.
you're going to get an error because that'll be a negative argument.
That's why I said, usually if you get an error message, it's because you messed up. Okay? And that was it. We messed up. We should have put that parentheses right there.
We use, think about this. To solve exponential equations, we use logarithms. To solve exponential equations, we use logarithms. Now we're going to start solving logarithmic equations. To solve logarithmic equations, we're going to use what? Exponential equations use logarithms. Logarithmic equations use exponents. That's right. Logarithmic.
Tim, I haven't typed in the answer. 2601.
Okay.
Just to give you an idea.
Logarithmic
Here's what we're
equations.
starting now.
Switch to my paper. I need to write a little.
There.
We solved logarithmic equations the last time, just a few of them, very briefly at the beginning, before we started expanding and condensing. I hope you remember.
1, 2, 3, 4. I think it was.
Do you remember what we would do? We'd have a single log equals a number, and we'd take the base of that logarithm. We'd turn the logarithmic equation. We'd use exponents by turning all of the original problem into exponents, and then 3 to the log base 3 are inverse functions, and they cancel themselves out. So we're going to turn the logarithmic equation into the power on an exponential equation. But in order to do that, you must make sure that the equation is in the form. And if it's not, you'll have to condense to get it in that form. Equation must be in the form single logarithm equals a number. Single logarithm equals a number. You need the equation in the form so that you have a single logarithm on one side and just a number on the other side. In that event, you then turn that statement into powers using exponents. Whatever the base of the logarithm is, that's the base of the exponent. I'll say use, I don't know if I need
both sides to the same power as the base.
No, because then this stuff would become into exponents. This becomes an exponent with the base, the same base of the logarithm. That sounds too convoluted. Let's just look at an example. Let's see if we can do it without writing out those steps. This is number 5. Log base 6. Is that a 5x minus 5? Log base 6 of 5x minus 5 is equal to 3. That's a log base 6. this is already in the form we need. We don't have log plus log or log minus log. It's a single logarithm equals just a number on the other side. We're going to take the base of that logarithm, use it as the base of the exponent. 6 to the log base 6. They're inverse functions. They cancel out, leaving you just that 5x minus 5 equals 6 cubed. Is that 216?
Mm-hmm.
Even though it looks funny, that's saying 6 cubed. 6 times 6 times 6 is 216. The 6 to the log base 6 cancels out, leaving you the argument 5x minus 5. Well, this might be the easiest equation we solved so far. We're not going to have to use our calculator and get decimal approximations. We know what we need to do to get that x by itself. What will I do first? Add 5 to give me 5x equals 216 plus 5 is 221. And then divide by 5 to give us x equals 221 all over 5. There is one problem though. We need to make sure the thing that follows the logarithm must always be positive. The argument has to be positive, or else you're going into imaginary numbers. If you take that 221 over 5 and you plug it in there for x, do you get a positive argument? The exact value doesn't matter, just is that argument positive? You have to take that number and plug it into the argument and make sure that the result is positive. And yes, it is. You'd get a 216 in that event. So 221 is an acceptable answer.
Let's see a better illustration of what.
Suppose, okay, before we go on, once I've written that down, then I'm going to change this up. Suppose we've gotten x equals 1/5. Suppose we got 1/5 as our answer.
Or 0.
5 times 1/5 minus 5. 5 times 1/5. The 5's cancel. That's a 1 minus 5. Is that positive? If x were 1/5, would that argument be positive? No. So just because you get a positive x value doesn't mean that it's an acceptable solution. You have to make sure that once you plug it into that argument, you get a positive number. I'm going to say, note, be sure to verify that your solution gives a positive argument.
Now, sometimes you might want to use a calculator if you don't like working with the fractions. 221 over 5 is the decimal number 44.2. 5 times 44.2 minus 5.
Clearly that's positive. You don't even have to punch it into your calculator. The exact value doesn't matter. Just make sure that the thing you get there is positive. Any questions? Number 6. Hopefully you remember how to condense logarithms. That stuff we were doing the last time. We have a log base 6 of x plus log base 6 of x minus 5 is equal to 2.
Log base 6x plus log base 6x. Okay. Show them that little statement, the form you wanted in.
the form you want it in. You want it in the form single logarithm equals a number. You don't want log plus log. You don't want log minus log. Unfortunately, here we have log plus log. So we're going to have to condense these logarithms. We have a log base 6. Now I remember doing this a week ago. When we were condensing, I'd ask myself, do I need a fraction bar? In this case, the answer is, what do we look at to make that decision? I've slept since then, and so we all have. Let's see. Here we are condensing. Hey, this first one, y'all remember that? What did we look at? We had a fraction bar when we condensed it. What did we look at to decide if we needed a fraction bar? That minus sign there. So that minus sign says you're dividing. Hey, look at this. Here the logarithms were being added. Did we have a fraction bar? Did we divide the y and the z? No, when they're being added, what do you do to the arguments? You're not dividing, you are multiplying.
Oh, look at
so
16. Look at that.
There it's added, so you multiplied the x and the y, then subtracted, you divided by the z. Y'all remember doing that? Okay, so I asked, do we need a fraction bar? And y'all said no. So what does that mean we're going to do to these arguments? If you're not dividing, you have to multiply x times x minus 5. Notice there were no exponents to deal with, no coefficients, to move up as exponents. The logarithms are being added, so we multiply the arguments. I claim we now have the form that we want. Single logarithm equals a number. Single logarithm equals a number. It looks like number 5, doesn't it, at this point? So we'll use whatever that base is, 6. That's what we're going to use here. We have a base 6. Turn all of this stuff into exponents. The base will be 6 and 6. Let's do the right side first. The right side is the quickest side. What's the right side going to reduce to? It looks funny. What's that saying? Okay, 6 squared is 36. The 6 to the log 6 cancels out. What are we going to have to do here inside those brackets? X times x minus 5.
Okay.
6 squared became 36. The 6 to the log 6 canceled. But we have x times x minus 5. What are we going to have to do there? Distribute. X times x is x squared minus x times 5 is 5x. We haven't had to solve a quadratic equation in a while, have we? It's quadratic. We need to get it set equal to 0, so what do you think I'm going to do? Move the 36 over, so x squared minus 5x minus 36 is equal to 0. And I think this is factorable. It's a simple trinomial. Those are the nice ones to factor, because x times x, what's the only thing that we could use to get x times x? X squared. What's the only thing we could use to get x squared? I think I accidentally said it, didn't I? X times x. What do we know about the signs? Last sign's a minus, so a plus and a minus. I'll go ahead and write them down. And then 36. Let's see, we could have 1 times 36, or 2 times 18, or 3 times 12. Is there another one?
9 and 4.
4 times 9. Is there another one? 6 times 6. For a simple trinomial, you choose the pair that, in this case, subtracts to give you 5. Which one is it? 4 and 9. Now play it out in your head to get a minus 5x. What should I put after the x plus? Should I put the 9 or the 4 here? Put the 4 there, the 9 there. This is week 13 and we're still having to factor. I said at the beginning of the semester it'd never go away. Set each factor equal to 0 to give us x equals here -4, or x equals here +9. Do not forget, you have to verify that your solution gives a positive argument. Gives only positive arguments, okay? Okay, -4. You plug that in for that argument. Is it a positive number? No, it's right off. It's negative. -4 minus 5, that'd be -2. But as soon as we see that you plug in that -4, that argument's negative, you cross it out. What about 9? Plug in 9. Is that positive? 9 minus 5, is that positive? So 9 is the only acceptable solution.
Most of the time, you mark out the negative numbers. Okay? Not always.
Suppose we've gotten 3. Would 3 be okay?
Would 3 be an it'd be okay here.
Every argument has to be positive. Look at that second argument. If we'd gotten x equals 3. 3 minus 5, is that okay? No, so just getting a positive x value doesn't mean it's going to work, okay? You may still have to cross it out. But most cases, if you get a negative solution for these logarithmic equations, you have to discard that answer.
And it's even possible that you could get 2 negative numbers and none of them would work, in which case the empty set.
But that is extremely rare. Those problems would have to be rigged very carefully so that you get 2 extraneous solutions. Remember, an extraneous solution is a solution that you get and then have to cross out. Any questions there? Number 7.
All ready to move on? Any questions?
Number 7. Oh, let's see. Am I going to have room for this number 7 there? You know I write big. You know I'm not going to take a chance. I'm going to move on.
I was looking. It looks like your notebook will have plenty of paper for the semester.
Yeah. Mm-hmm. So this is number 7.
Hey.
Oh, look at this.
Is there something missing here? There's not the little subscripts. Y'all remember what we what we assume the subscript is?
If you see log without a subscript, what do you assume that base is? Because you need to know that, because that's what we're going to use as the exponent base to cancel out that log. I'll give you a hint. It's called the common logarithm when you don't have a subscript down there. Who remembers what that subscript is? No, it's a number. Log base b. B would equal what? Years and years. 10, yes, because back in the olden days, we just love to talk about them olden days, don't we? Okay. So where did I write that the last time? Let's see. two special logarithms. If you see log without a base and without a subscript, you assume it's a base 10. Okay? There's another problem wrong with this. Is this equation in the desirable form? Can I put a 10 and a 10 and cancel out the logs?
Is it in the form single logarithm equals number?
And needs to be in the form single logarithm equals a number. I can get the equals a number pretty easily. I can get it equals 1 by itself on the right side by picking up this second logarithm and moving it over to the left. So we'll have a log of 4x plus 3. That's going to become I'm moving this plus log x minus 3 to the left. That'll change that plus to a minus log x minus 3. It only changes the sign in front, not the sign in the argument, is equal to 1.
We're doing the most basic problem-solving strategy. You're trying to make number 7 look like number 6. You know how to do number 6 when it was 2 logs equals number.
Now we still don't have the desired form. We want a single logarithm equals a number. We have the equals a number. What are we going to have to do to get a single logarithm?
How do we condense this?
I'm going to write the log, and then I'll ask the question, do we need a fraction bar? And your answer is yes, because of the okay, right there. This minus right here, that minus is the reason we need that fraction bar. What have we got on top? Four x plus 3, and on bottom, x minus 3. And now, this is the desired form. Single logarithm, y'all have log plus log or log minus log, equals a number. Everything written there is about to become exponents. What will I write as the big base here to cancel out that log? Normally we use the subscript that's written there. Normally we would use the subscript that's written there, but there's not a subscript. So, what do we use?
What subscript do we assume is there?
10, okay. 10, okay, that's a little, assume 10 there. 10 to the common log cancels out, leaving us 4x plus 3 all over x minus 3. What have we got on the right side? What's that going to reduce to? 10 to the first power is just a 10. Maybe, you know something, we have to solve this fractional equation. Look what I'm going to do. I'm going to put that as a 10 over 1. Does that give you a hint on what I'm going to do to solve this equation? Be more specific. How am I going to multiply? Cross multiply, that's right. Cross multiply, there and there. 4x plus 3 times 1, well that doesn't get easier, it's just 4x plus 3. Equals, we have to take the 10 and multiply it by x minus 3. What's that going to give us? What do we have to do with that 10 and the x minus 3? Starts with a d. Distribute. 10 times x is 10x minus 10 times 3 is 30. We have to get all the x terms on the same side. I think it'd be easiest to get the x terms right here on the right hand side. It'll decrease the number of negatives, that's for sure. So what will I do to get that 4x on the right hand side? Or what will I do with that 4x to combine it with that 10x? 10x minus 4x gives me a 6x. What am I going to do with this minus 30? Add 30. 3 plus 30 gives me a 33. And then divide by 6. Divide by 6 to give us x equals 33 over 6. There's a common factor there that we could cancel out. What is it? We can cancel a 3 above and below. 33 divided by 3 is 11. 6 divided by 3 is 2. But remember, we have to make sure. Look back at the original problem. Every one of those arguments has to be positive. 11 halves. You know something? It might be easiest just to think of it as a decimal. 11 halves is what? 5 and a half, so 5.5. 4 times 5.5. That'd be bigger than 20 plus 3. Something bigger than 20 plus 3, that's positive. What about 5.5 minus 3? Is that positive? It's positive. So is 11 halves an acceptable solution? Yes, it is. Suppose we'd gotten x equals 2. Would 2 have been acceptable? No, because 2 minus 3 is not positive. Well, you only got one possible solution, and it is acceptable. 11 halves.
I'm just curious about something.
What?
You do this, does it just say wrong, or does it say you haven't reduced it? Although
it's equal, it's not in the correct form. That's very nice then, okay? So they're warning you here in the homework. They wouldn't do that on a test, though, okay?
Make sure your answer is simplified and entered in fully reduced form.
Okay, so change it to 11 halves.
Just delete all of that. 11 over 2.
Any questions?
So, if you have a logarithm on each side, put them on the same side, and then do that condensing. Now, if you haven't done the logarithm stuff from a week ago, once you do, this condensing stuff won't be such a mystery here. Okay?
Number 8. Number 8. Okay. Log base 2 of x plus 7. 2 of x plus 7 plus log base 2 of x minus 7 is equal to 5. Log base 2 of x plus 7 plus log base 2 of x minus 7 is equal to 5. Hey, this equation is half right. We have the equals a number by itself. That's nice. But here we have log plus log, so we're going to have to condense that. I'm going to write my log base 2. Log base 2. Do I need a fraction bar? No. Well, wait a minute. I see a minus there, but that's not the minus you look at. You're looking at the sign in front of the logarithm, the sign that connects the logarithms. That's a plus, so you're not going to divide. The only other option, if you're not going to divide arguments, you have to multiply. So you have x plus 7 times x minus 7. There. Oh, this pen is going dead. Okay, there. And now I think we have the desired form. We have a single logarithm equals a number. You don't have log plus log or log minus log. So all of this stuff that I have written here is about to become an exponent. What will I use as the base? will I use as the base? 2. Okay, I agree. 2 and 2.
On the right side, don't think 25. That's a common mistake.
Actually, it is. You're right. But 2 to the 5th, is that 32?
Mm-hmm.
2 times 2 times 2 times 2 times 2.
It's like 8 times 4.
That's 32. 2 to the 5th became 32. What's going to happen over here? Just tell me in words what's about to happen. The 2 to the log base 2 cancels out. And we have x plus 7 times x minus 7. What are we going to have to do with this x plus 7 times x minus 7? Okay, we have to FOIL that out. Get rid of those parentheses. First, we have x squared, outer, minus 7x, inner, plus 7x, last, 7 times negative 7 equals 32. This is working out very nicely because something's about to disappear. What is it?
7x.
The 7x's, I agree. You know something? We haven't used the square root method in a long time, have we? Something squared equals a number. We can move that 49 over and then set this up to use the square root method. The other option is get it set equal to 0 and factor using the difference of two squares. I think we need to practice with that square root method. So I have an x squared on the left. What am I going to have to do with this minus 49 to combine it with the 32? Add it. 32 plus 49 is giving me an 81. And when you use the square root method, you can only use it if you have something squared equals a number. But you can't have a variable over here and use the square root method. And so we're going to we drop the square on one side. And remember, we pick up a positive and a negative square root on the other side. And we know the square root of 81 is... Now, are both of those answers going to be acceptable? Is 9 and, are both of them acceptable? 9 and negative 9? Take 9. 9 plus 7, that's positive. 9 minus 7 is positive. So positive 9 is okay. What about negative 9? Negative 9 plus 7, no, that is not positive. But since most of y'all would have forgotten the plus minus anyway, come on, be honest. How many of y'all would have forgotten the plus minus and just gone to the square root of 9? You would have been okay.
Yeah.
You would have been okay if you forgot the plus minus. In this case, you would have been okay.
I'm wondering, where is that plus minus when we did it?
When we were solving exponential equations,
Okay.
Solving quadratic
Keep going.
equations. Y'all remember that? Here we solved, let's see, that's factoring and...
Oh, that's still the previous.
There it is. Y'all remember the square root method?
We'd have to say plus minus 5 here.
But here, that negative 9 wouldn't have worked anyway. You have to discard it. Now, I like problem number 9. Oh, type in that answer. If 9 is what I think it is, then that's a really good problem. 9 is the answer also.
Okay.
Okay, look at this. Don't say anything, just be thinking about it. And log base 3 of log base 3.
You told me not to say anything, but I am going to say something.
Oh, I wasn't telling you not to say anything. I was saying that to you, okay? I thought you were going to jump in and spoil the surprise. Okay.
Surprise.
Log base 3 of log base 3 of x equals 1. Okay, switch. Okay, what were you going to say, Tony?
Does this look different from the other problems we've done?
I see two log notations.
But it's log. Have we had log any time here?
I said you can't have log plus log minus 1. You need, I guess when I wrote single logarithm, I should have written single logarithmic term. Okay? I claim that this problem here, just ignore that argument. You don't have log plus log or log minus log. It's already in the desired form. You have a single logarithm, a single logarithmic term equals a number, not log plus log or log minus log. So just ignore what's in those parentheses. We have a single logarithm equals a number. I claim we can get rid of this log base 3 by turning everything into exponents. I'm going to ignore it. I'm getting rid of it. Why don't I have something little bitty that I can put on there to cover that up? I can do it like this. I'll put a 3, and a 3. No, let's see if I can cover. What's inside there doesn't matter. That's what I'm trying to say. The argument doesn't matter. We have a single logarithmic term. At this point, we can use inverse functions. 3 to the log base 3 cancels out. Oh, that's better. Okay. So, there. Okay. So, just ignore what's inside those parentheses for the time being. This is a single logarithm. Single logarithm equals a number. We put the 3 in the 3. 3 to the first power. I know what that is. It's just 3. What's going to happen here? It cancels out, and at that point, this stuff here comes into play. It floats down or drops down to be a log base 3 of x equals 3.
Oh, your green thing.
Okay, there.
Oh, I like it.
I think it's a little pale, but still. Any suggestions on what we're going to have to do now?
Want to get the x by itself.
We want to get the x by itself, and we got to cancel out that log notation.
Cancel the first log. You used a big green 3.
What do you think we'll do here? Use a big red 3. 3. 3 to the log base 3 cancels, leaving us what on the left side? Now, that's on the right side. 3 cubed is 27, okay? And on the left side, we just have an x. This is the only type of logarithmic equation where you could have had different bases. It would have been a better problem if we'd had different bases. We could have had a 3 and a 4, but there's no reasonable realistic explanation where I could think of why you would want to have two logarithms with different bases in the same problem. It's just not done. There's no realistic reason why you would want to do that.
If you have log base 3 and 1, everything's going to be base 3. So first, can you tell how this one differs from problem 8 or any of the others?
The ones that have multiple logs before now have been log plus log or log minus log, and we had to condense.
But this is log.
Log. No. This one here is the log of the log. We don't have log plus log or log minus log. I claim that is a single logarithmic term equals a number. Start getting rid of the log notation, working your way from outside to inside. And obviously, if you plug in 27 there, that x is going to be positive. So 27 is an acceptable solution. Any questions there?
think number 10 is the last one. Once you hit number 11, it's all review. Oh, I like that problem.
Number 10. Okay. Log base 8 of x plus log base 8 of x minus 12 is equal to 2. Log base 8.
There's nothing unusual about this problem. It's very similar to one we've already done. But I didn't want to have fewer than 10 problems, so that's why I put this one on there.
Okay. There was really only one correct first step. What is it? Switch to my paper.
Oh. It's number 7.
Well, still, I'm going to let
Look
him.
at number 7.
What do y'all think I'm going to do? Condense, I heard we already have the equals a number, and so we need to condense these logarithms. So I'm going to write my log base 8
Another reason I
notation.
put this problem next is I wanted to make sure y'all see the difference and don't get carried away with number 9 and just start going 8, 8, without doing this condensing. Okay? Hopefully you see how it's different. Log log versus log plus log.
Well, what are we going to do to the x and x minus 12? We'll either have to divide them or multiply. Which one? Multiply because they're being added. I agree. So we'll have an x times an x minus 12. And now what can I do? Everything written here is about to become what? Exponents. What will I use as the base? 8. I agree. 8 and 8. 8 to the log base 8. That cancels out. We have x times x minus 12. What will I do there? Distribute to give me an x squared minus 12x. I should have already asked y'all this. What have I got on the right hand side? 8 squared is 64. That's saying 8 squared. Don't let the fact that the 2 and the 8 are the same size shock you. It's just saying 8 squared. It's quadratic, which means we better get it set equal to 0. So we have x squared minus 12x. That'll become a minus 64 equals 0. Oh, it's a simple trinomial at least. I hope I don't run out of room. Am I going to run out of room? Hopefully not. I'll write my 2 sets of parentheses. I'm just a big printer. I'm a big writer. I use up a lot of paper. X squared, it's a simple trinomial. We know what times what's going to give us x squared. What am I going to write here? X times x. What do we know about the signs? Right? Okay, so that last sign's a minus, so you have you have one of each. One positive and one negative. That last sign's a minus, so you have one of each. Now 64, don't use 8 times 8, because remember, the pair you use has to subtract to give you what? What number? 12, that middle one. Well, let's see, there's 1 times 64, 2 times 32, 3, 4 times 16, 5, 6, 7, and then 8 times 8. Which pair will we use? 4 and 16. I agree. Now play it out in your head when the outer and inner has to give you back a negative 12x. So where should the 4 go? Where should the 16 go? You tell me what's going to go after the x plus.
4.
The 4 and then the 16. I agree. That would be a negative 16x plus 4x gives me the negative 12x. Any questions up to this point? So we set each factor equal to 0. X plus 4 equals 0. X minus 16 equals 0. What's this first equation going to give us? X equals negative 4. Okay. The second one? Okay. Are they both acceptable solutions? No. Which one am I going to cross out? Negative 4, if you plug it into that argument, you have the log base 8 of negative 4. That is not allowed. Or if you check here, negative 4 minus 12, either one, you're going to get a negative argument, discard it. But 16 is positive, 16 minus 12 is positive. So 16 is acceptable.
Notice he circled X equals, but all you type in is 16.
Yeah, you're right. I should not have done that.
No, I mean, any questions? Here we get to that little, and the domain of F is equal to the range of F inverse.
The range of F is equal to what? The domain of F inverse. Okay.
Well, enough of that.
Okay.
Going back.
Any questions?
Oh, well, looking at that.
Any questions? Provided you remember how to condense logarithms, then this isn't that bad. It's certainly not as bad as that last assignment on logarithms that took us over 2 hours.
Well, those problems weren't really hard, Tim. It was just a lot. 20 problems.
Good. Okay. Yeah, I know. I didn't say it was.
Oh, okay. Any questions? Are we ready for me to stop recording? Here goes.